All right, everyone. As we begin Chapter 5, we're stepping into the heart of what makes PLCs so powerful, programming logic. Up to now, we've looked at what a PLC is and how it connects to field devices. Now we'll see how we actually tell it what to do. By the end of this chapter, you should be able to define and describe the PLC memory map, explaining how memory is divided into program and data areas. Explain input and output image tables, and identify the different types of data files. Describe the sequence of operations in the PLC program scan sequence. Explain communication between ladder logic and the processor, showing how input conditions are converted into logic decisions and output actions. Define and apply internal relay instructions, such as latches, unlatches, and control relays for internal decision-making. Identify the common operating modes of PLCs, program, run, and test, and describe when each is used. Develop basic ladder logic programs. Although the fundamental concepts of PLC programming are similar across manufacturers, differences in memory organization, I/O addressing, and instruction sets mean that PLC programs are not directly interchangeable between brands. Even within the same manufacturer's product line, models may differ in how memory and addresses are structured. The memory map, or memory structure, of a PLC processor is divided into several areas, each serving a specific purpose. Allen Bradley PLCs, for example, use two primary memory organization methods: rack-based systems and tag-based systems. The RS Logix 500 family uses a rack-based, fixed memory structure, where I/O addresses are determined by the slot location of the input and output modules within the PLC rack. The RS Logix 5000, or Studio 5000, family uses a tag-based memory structure, which assigns names, tags, to memory locations instead of fixed numeric addresses. Tags make it easier to identify variables and improve program readability. In tag-based systems, memory is not divided into fixed areas for inputs, outputs, or data. Instead, memory is allocated dynamically as tags are created. This chapter focuses on the memory organization for rack-based systems. Inside every PLC, the processor's memory is divided into different sections, and one of the most important is the program file area. This is where your ladder logic program is stored, the actual instructions that tell the PLC how to control the system. If you look at the diagram on the left, you can see several memory sections, system functions at the top, some reserved areas, and then the user program section. That's where we write our ladder logic, and it makes up most of the PLC's total memory space. In the RS Logic software, these program files are organized in a list like you see at the bottom left. sys0 and sys1 handle system-level tasks, while LAD2 is our main ladder file. By default, the PLC always starts execution with LAD2 every time it runs through its scan cycle. Now, over on the right side, you can see an example of a ladder logic program stored inside one of those files. Each rung represents a small piece of logic. Inputs on the left, outputs on the right. When the input conditions are true, the PLC energizes the output coil. So in short, the program files are the heart of the PLC's memory. This is where your logic lives, and it's what the processor executes continuously during operation. Now that we've seen where the PLC stores the ladder logic program, let's look at where it keeps the data that program works with. That's what we call the data file section of memory. Each PLC keeps organized folders or data files for different kinds of information: inputs, outputs, timers, counters, integers, and more. You can see that list on the left side of the figure. The output image table, shown in the top window, holds the on or off status of every output. A 1 means the output is energized, and a 0 means it's off. This table is constantly updated as the PLC executes the scan cycle. Below that, the counter table shows how timer and counter instructions store their information. Things like the preset value, accumulated count, and whether the counter is done. So, while the program files contain the logic, the data files hold the real-time information the PLC uses to make decisions. You can think of it as the PLC's memory banks. It remembers everything happening in the process, one scan at a time. Here we can see how the PLC organizes its data files. Each one is like a folder that holds a specific kind of information. At the top, we have the output file O0, which stores the on-off states of all outputs. Next is the input file I1, which holds the status of every input device connected to the system. Below that, you'll see files for status, binary bits, timers, and counters. These are all internal memory areas used by your program. For example, the timer file T4 stores values for the preset and accumulated time, and the counter file C5 holds count data and status bits. You'll also see integer and floating point files. These are used when you need to store numbers or perform calculations. So, the key takeaway here is that each data file is organized by the type of data it stores. This makes programming and troubleshooting much easier because you always know where to find your inputs, outputs, timers, and internal bits. Now let's take a look at how the PLC keeps track of every input and output device in the system. In a rack-based PLC, each input or output terminal has a unique address. The format looks like this: I:1/2. The first letter, I or O, tells us whether it's an input or an output. The number after the colon is the slot number, which refers to the module's physical position in the rack. And the number after the slash is the bit number or the specific terminal on that module. So for example, I1/2 means input module in slot 1, terminal 2. O2/11 means output module in slot 2, terminal 11. The PLC uses these addresses to organize all input and output data in memory. When it performs the input scan, it checks every I address to see which inputs are active. When it performs the output scan, it updates every O address to turn devices on or off. This addressing system gives us a one-to-one link between the physical wiring in the control cabinet and the logic symbols in the ladder diagram. Let's talk about how the PLC keeps track of which outputs should be on and which should be off. Inside the processor's memory, there's a special section called the output image table. This is where the PLC stores the on-off status for each output point. Each bit in the table represents one output terminal on the module. When your ladder logic says an output coil should turn on, the PLC doesn't instantly energize that output. Instead, it sets that bit in the output image table to a 1. Then, during the output scan, the PLC updates the actual output module to match the table. If the program calls for an output to turn off, that bit is set to 0, and the corresponding device de-energizes. So in short, the output image table acts as a digital memory mirror for your output modules. The PLC writes ONs and OFFs into memory, and the hardware updates to match those values each scan cycle. The scan is normally a continuous and sequential process of reading the status of inputs, evaluating the control logic, and updating the outputs. This figure shows an overview of the data flow during the scan process. For each rung executed, the PLC processor will examine the status of the input image table bits, copy the status of all of the input terminals to the input image table. If an input is active, the corresponding bit in the input image table will be set to a 1. Solve the ladder logic in order to determine logical continuity. Update the appropriate output image table bits if necessary. Copy the output image table status to all of the output terminals. Power is applied to the output device if the output image table bit has been previously set to a 1. This slide shows how a PLC scans and executes ladder logic instructions, a fundamental concept for understanding how PLCs think and process programs. The processor scans the ladder diagram in a very specific order, from left to right and then top to bottom. You can see in this diagram that each rung is read horizontally, beginning at the left power rail and ending at the right. As the PLC moves left to right, it evaluates each input instruction on the rung. If it finds a continuous path of true conditions, the output coil on that rung is energized. If any instruction is false, the path is broken and the output remains off. Once the PLC finishes one rung, it moves down to the next one and repeats the same process, all the way down until it reaches the Yindi instruction. After that, the entire program starts over again, thousands of times per second. So remember, the PLC always scans left to right, top to bottom, and the order of your instructions determines how your program behaves. Now that we understand how the PLC stores input and output data, let's look at how it actually processes that information. The PLC runs through what's called the program scan cycle. This cycle repeats over and over while the controller is in the run mode. It starts with the input scan, where the PLC reads every input device, push buttons, switches, and sensors, and saves their status into the input image table. Next, it performs the program scan, where it runs your ladder logic one rung at a time, using the stored input data to decide which outputs should be turned on or off. The results of that logic are written into the output image table. Then comes the output scan. This is when the PLC updates the actual hardware outputs, energizing or de-energizing field devices to match the output image table. Finally, the PLC performs some housekeeping tasks, checking memory, communications, and internal diagnostics before starting the next cycle. This entire sequence happens incredibly fast, often several thousand times per second. So, every few milliseconds, the PLC is rereading inputs, solving the logic, and updating outputs, keeping your system running smoothly and in real time. In the next lecture, we will take a brief look at the various PLC programming languages.